13 billion years ago, before most of the galaxies you can see in any photograph of deep space had even finished forming, something already existed that, by every rule astronomers thought they understood, should not have been possible yet. Not a star, not a young, growing galaxy slowly building itself up over time. A black hole so massive and so disproportionately large, compared to everything around it, that it makes up at minimum 2/3 of the entire mass of the structure it's sitting inside. Not 2/3 of a galaxy's central bulge, 2/3 of the whole thing. For the first time in the history of astronomy, scientists just measured that mass directly, not estimated it, not inferred it, from assumptions borrowed from the modern universe, but calculated it the same way you'd calculate the mass of the sun from watching planets orbit it. And what that direct measurement revealed is forcing one of the most respected astrophysicists in the field to call this a total paradigm shift in how we think black holes are born. This is the story of QSO-1, one of the most massive objects relative to its surroundings that James Webb has ever detected, and why finding it has upended a scientific assumption that has stood for decades. I'm your host, and this is your channel. If you want the real science behind the biggest discoveries in space, subscribe now, because we're just getting started. To understand why this discovery is being called a paradigm shift rather than just another interesting data point, you first need to understand the specific scientific problem it solves. A problem that has genuinely puzzled astronomers since the James Webb Space Telescope became operational in 2022. For decades, the conventional understanding of how supermassive black holes form followed a fairly logical step-by-step sequence. A galaxy forms first. Large stars within that galaxy burn through their fuel and eventually collapse under their own gravity, forming relatively small, stellar mass black holes. Over enormous stretches of cosmic time, those smaller black holes merge with each other and gradually feed on surrounding gas and dust, slowly building up mass until, after billions of years, you end up with the kind of truly supermassive black holes we observe at the centers of galaxies today, including our own Milky Way. It's a model that makes intuitive sense, and it fit reasonably well with everything astronomers had observed in the relatively nearby and therefore relatively recent universe. The problem is that Webb kept finding supermassive black holes that simply didn't have enough time to form that way. Since becoming operational, the telescope has detected thousands of black holes in the early universe, and several of them, sitting at distances corresponding to less than 700 million years after the Big Bang, already possess masses ranging from millions to billions of times the mass of our Sun. Building a black hole to that scale through the traditional gradual process of stellar collapse followed by slow merging and feeding simply doesn't work within that kind of time frame. There hasn't been enough cosmic history for the traditional mechanism to produce something that large. Scientists have been aware of this puzzle for years, and it's remained one of the most significant open questions in modern astrophysics, a genuine crisis for the standard model of black hole formation. What makes the specific object at the center of this story so important is that it finally gave researchers a way to test that puzzle directly, rather than relying on the same kind of indirect, assumption-based estimates that had been used for every other early universe black hole detected so far. The object is called Abell 2744 QSO-1, or QSO-1 for short, and it belongs to a strange, relatively newly identified class of objects nicknamed Little Red. Dots, extremely distant, extremely compact sources that have become one of the most tantalizing mysteries to emerge from Webb's deep field observations. QSO-1 existed just 700 million years after the Big Bang, and remarkably, its entire visible structure spans only about 1,300 light-years across, genuinely tiny by galactic standards. Its light has been traveling toward us for more than 13 billion years, meaning we are seeing this object exactly as it existed in the very early universe, essentially a fossil snapshot of conditions that no longer exist anywhere in the observable cosmos today. QSO-1 happens to sit in a fortunate position for astronomers, directly behind a massive foreground galaxy, a cluster called Abell 2744, nicknamed Pandora's cluster because of the sheer complexity and violence of the galactic collisions that formed it. The cluster's enormous gravitational field acts as a natural magnifying lens, a real physical phenomenon called gravitational lensing, bending and amplifying the light from anything positioned behind it. Because of this effect, QSO-1 doesn't just appear brighter and easier to study than most other little red dots Webb has found. It actually appears in 3 separate locations in the sky simultaneously, 3 distinct magnified images of the same distant object, produced entirely by the lensing effect of the cluster sitting in front of it. Earlier studies of QSO-1, conducted before this latest research, had already suggested something remarkable, that the object might be little more than a glowing cloud of hydrogen and helium gas swirling around an already enormous black hole, estimated at roughly 40 million times the mass of the Sun. But there was a serious problem with that early estimate, the same problem that has haunted essentially every other early universe black hole mass measurement Webb has ever produced. Francesco D'Eugenio, a co-author on the new research from the University of Cambridge, explained the issue plainly. Before this study, every single mass measurement of a black hole in the early universe had been indirect, built entirely on assumptions borrowed from how black holes behave in the much closer, much more recent universe we can study in far greater detail. Nobody actually knew for certain whether those nearby universe assumptions held up correctly when applied to conditions that existed less than 1 billion years after the Big Bang itself. So the research team, led by Roberto Maiolino at the University of Cambridge, set out to do something that had never been accomplished before for an object this distant: measure the black hole's mass directly, using nothing but basic, well-understood physics, rather than relying on assumptions at all, using the integral field unit on Webb's near-infrared spectrograph, an instrument capable of simultaneously capturing detailed spectral information across many individual points within an object. Cambridge graduate student Ignace George-Ballis and Cosimo Marconcini of the University of Florence mapped the motion of hydrogen gas swirling in the region immediately surrounding QS01's central black hole. When they plotted how quickly that gas was rotating at different distances from the center, they found something scientifically decisive. The gas exhibited what's called Keplerian motion, the exact same predictable orbital pattern that governs how planets orbit our own sun. A clean, mathematically precise relationship between distance and orbital velocity that only occurs when almost all of the surrounding mass is concentrated in a single central point, rather than spread out across a large population of stars. George-Ballis explained why that specific detail matters so much. If QS01's mass had been spread out across a substantial population of stars, the way mass is typically distributed within an ordinary galaxy, the surrounding gas simply would not exhibit this kind of clean, perfect Keplerian rotation. The fact that it did told the research team with real physical certainty rather than assumption that the overwhelming majority of QS01's total mass is concentrated directly in the black hole sitting at its center. Because Keplerian motion is governed by simple, extremely well-established laws of gravity, first written down mathematically centuries ago, the team was able to use their precise gas velocity measurements to calculate the black hole's mass directly, using the same fundamental physics you'd use to calculate the mass of any star from the orbits of the planets around it. It was, in the researchers' own words, a feat that had not previously been possible for an object this distant, and the number that calculation produced was staggering. Not the earlier estimate of 40 million solar masses, but a directly measured mass of roughly 50 million times the mass of our Sun. More significant than the raw number itself, though, was what the mass represented relative to the rest of the object. The black hole makes up, at an absolute minimum, 2/3 of QS01's entire total mass, a proportion that is thousands of times greater than what astronomers observe in the black holes sitting at the centers of galaxies in our nearby present-day universe, where a central supermassive black hole typically accounts for only a tiny fraction of its host galaxy's overall mass. The team's spectral mapping revealed something else that reinforced just how unusual this object truly is. The gas surrounding QS01 is composed almost entirely of hydrogen and helium, with barely any trace of heavier elements like oxygen, the kind of elements you'd expect to find in abundance if the surrounding region contained a substantial population of stars and the accumulated stellar debris those stars leave behind over their lifetimes. QS01's measured metallicity, the astronomical term for the proportion of elements heavier than hydrogen and helium, came out to less than 0.5% of the Sun's own metallicity, making it one of the most pristine, chemically primitive galactic environments ever directly measured by any instrument. Maiolino described the overall result as a phenomenal finding, emphasizing that it represents the first direct measurement of a black hole's mass within the first billion years after the Big Bang, and that the number it produced lines up consistently with previous, less certain estimates, offering researchers real confidence that the assumption-based methods used to measure other early universe black holes likely haven't been dramatically overestimating their masses either. Here's why all of this adds up to a genuine paradigm shift rather than simply an interesting new data point. An object where a black hole makes up 2/3 or more of the total mass, sitting in an environment almost entirely free of the heavier elements, produced by generations of stars, simply cannot have formed through the traditional, gradual process of stellar collapse, followed by slow merging and feeding over time. There hasn't been a substantial host galaxy there to produce and feed it in the traditional sense. George-Ballis put the implication directly. The team appears to have found a black hole that lacks any substantial host galaxy, and that predates the normal stellar processes that are supposed to produce black holes in the first place. That is compelling evidence for something long theorized, but never before directly confirmed, either a so-called heavy seed black hole formed through the direct, sudden gravitational collapse of an enormous primordial cloud of gas without ever passing through an intermediate stellar phase at all, or an even more exotic possibility, a primordial black hole, one that may have formed within literally the first second of the Big Bang itself, long before any stars or galaxies existed anywhere in the universe. Maialino's own words capture the scale of what this means for the field. This finding, he said, is a total revisiting of the classical scenarios describing how black holes form and grow. Whether QS01's black hole ultimately traces back to a heavy seed formed from a collapsing primordial gas cloud, or to something even earlier and stranger, it was almost certainly born massive from the very beginning, and appears to be sitting in the early stages of slowly building an entire galaxy up around itself, rather than the other way around, essentially inverting the sequence scientists have long assumed governs how galaxies and their central black holes come into existence together. The research team doesn't believe QS01 is a lone, freakish exception either. Based on how frequently Webb has been detecting similar little red dot objects throughout its early universe surveys, the team believes objects like this likely weren't rare at all in the first billion years after the Big Bang. And researchers are now actively analyzing additional similar objects to determine whether supermassive black holes routinely predate the galaxies they eventually come to inhabit, rather than forming as a later consequence of galactic growth, the way the traditional model has assumed for decades. So here is where this genuinely leaves the field of astrophysics right now. A black hole measured directly rather than estimated, sitting less than 700 million years after the birth of the universe, making up at least 2/3 of the total mass of the tiny, chemically pristine structure surrounding it. A finding that one of the field's most respected researchers has explicitly called a total paradigm shift, not a minor refinement, and real direct evidence for a category of black hole formation, heavy seeds, or primordial collapse that had been theorized for years, but never definitively confirmed until this specific measurement became possible. That is not an exaggerated headline. That is the literal, on-the-record language NASA and the University of Cambridge used to describe their own findings, published simultaneously in Nature and the monthly notices of the Royal Astronomical Society in May of 2026. If this kind of story is what you come here for, one grounded in exactly what NASA's own scientists said and measured, rather than exaggeration, hit subscribe and turn on notifications, because there's a lot more of the early universe left for this telescope to reveal. Drop a comment telling me whether you think black holes really can form before their galaxies, and share this with someone who still thinks we fully understand how the biggest objects in the universe actually come into existence.